the orbitals will be hybridized here. We have seen the central metal, whatever the orbitals which are being involved in the coordinate bond, those orbitals has to be hybridized. It undergoes hybridization to form an equal energy orbitals. So during hybridization, it may take the d orbitals, that is, it may take inner d orbitals or it may take outer d orbitals also. So when it comes to outer d orbitals, so that is of 4d. So this is 3d, 4s, 4p and 4d. So 4d orbitals may be involved in few cases. So the 3d orbitals are going to involve, and in few cases 4d orbitals will be involved. If at all, if it is involving 3d orbitals, if 3d orbitals are involved, they are called as inner orbital complex, or those are nothing but inner orbitals. So the complex, if it involves the hybridization with a 3d, then the complex is called as inner orbital complex. If a 4d is involved, then we call that one as outer orbital complex. So we'll discuss this part once again with an example. Outer orbital complex. So inner orbital complex and outer orbital complex. Example let me give. So inner orbital complex, the hybridization will be D2 sp3 D2. It starts with a 3d, 3d2, s and p3. So for outer orbital complex, it is sp3d2. That is 4s, 4p and 4d orbitals are involved. So you can observe here 2, 3, d2, 3 and plus 3, it is 6. So 6 orbitals are forming. That is nothing but the coordination number of the complex is 6. So if at all, if the metal is showing d2 sp3, here also same thing, it is s1, p3 and d2, that is 1, 3, 4, 5 and 6. So coordination number 6 orbitals are there, means coordination number will be 6. So if 6 is the coordination number, it forms the octahedral complex, or the geometry is octahedral geometry. So hybrid orbitals, for hybridization, so the orbitals may involve inner d orbitals or it may involve outer d orbitals. So if it is inner d orbitals, we name that one as n-1 d orbital. If it is outer d orbitals, so we name that one as nd, general form, nd orbitals. If it is inner d orbitals, that is 3d orbitals, if it is involved, then we call that one as inner orbitals or inner orbital complexes. If at all, if outer d orbitals are involved, then it is called as outer orbitals or outer orbital complexes. So this is one point. Next point is, if at all, if the d orbital is considered, that is 3d. So in 4d we don't have any electrons there, because the transition metal, if you are considering, the first row will be with only 3d filled and 3d also not completely filled. So 4d will be empty only. So we are going to consider that one. Suppose if at all, if you are considering 3d orbitals. In this 3d orbital, suppose if this is the configuration, if the configuration is like this. Let us consider the configuration is like this. Then sometimes what happens is, sometimes the electrons, unpaired electrons of the orbitals may shift to this orbitals. So unpaired electrons. So if it is paired, then there is no change. No electron can come and accommodate in this orbital, because already in this orbital 2 electrons are there. An orbital can accommodate only 2 electrons. So unpaired electrons, if at all, if it is there, then electron from the one orbital may shift to another orbital. This may shift here. Then the electronic configuration may changes too. The electronic configuration may changes to. We'll do one thing so that it will be easy for you to understand. The electronic configuration may changes like this. And this is not going to happen in all the orbitals. These are 3D orbitals. So in 3D orbitals, sometimes the unpaired electrons may jump to the another orbital which is consisting of unpaired electron and which may get paired up. So if at all, if it is happening, then that is called as a rearrangement. Rearrangement of electron is going to take place. We call that one as a rearrangement of electrons. The electrons shifts this side, then these two orbitals will be made free. So if it is made free, then the hybridization, if coordination number is 6, then the two orbitals are empty here. This will be involved in the hybridization. Then it becomes D2sp3. Suppose if at all, if rearrangement has not taken place, then it will remain as it is. So the hybridization becomes sp3d2. So sp3d2, where it forms the outer orbital complexes. I hope it is clear. I'll repeat once again. So in an hybridization, we know that the metal while forming a coordinate bond, it should undergo hybridization. During hybridization, it may involve inner d orbitals or it may take outer d orbitals also. If it is taking inner d orbitals, that is n-1d orbitals, then the complexes are called as inner orbital complexes. If it is taking outer d orbital, then it is called as outer d orbitals. Outer orbital complexes. So when it is undergoing the hybridization, sometimes, so if at all, if the d orbital, inner d orbital is with unpaired electrons, then the electron may rearrange itself. So why it is undergoing a rearrangement is what I will study that one next. So when ligand approaches the metal, it happens when ligand approaches the metal. When ligand is going to approach the metal, few ligand has the capacity to shift these electrons. Because of the influence of those ligands, the shifting of electron will take place and the electrons get rearranged in this manner, so making the inner d orbitals vacant. So the ligands which has ability to rearrange, to cause an rearrangement in the inner d orbitals, those ligands are called as a strong field ligands. The strong field ligands, in the presence of strong field ligands, the unpaired electron gets shifts and it rearranges in such a way that there will be one or more vacant inner d orbitals will be made. So those inner d orbitals will be involving in the hybridization and it will be forming inner orbital complexes. So this happens only when the ligand is an strong field ligand. Then what happens if it is an weak field ligand? Weak field ligand, if it is an weak field ligand, then no rearrangement takes place. So the electronic configuration 3D orbitals remains as it is. The vacant orbitals will be from 4s, 4p and 4d orbitals. So these orbitals will involve in the hybridization and it will form the coordinate bond with the ligands. So this is about the basics of or the main postulates of valence bond theory. So we shall move on to the points now. So these are the few basic things I have written. So we can a few more things will write those points and we shall check them. The postulates we shall see. The central metal ion in the complex makes available a number of empty orbitals for the formation of coordination bond with suitable ligands. The number of empty orbitals made available is equals to coordination number. So this is the first point. So we have discussed this one earlier. That is, central metal is forming a coordination bond with the ligand. So central metal is forming a coordination bond with the ligand. So to make that bond formation, it require number of empty orbitals. That is nothing but vacant orbitals. So for making the vacant orbitals, so it will be what how many vacant orbitals it require? It require the number of vacant orbitals, which is equal to coordination number. Next, so that is the first point, central metal. So central metal want to make a coordination bond with ligands, it should require number of empty orbitals. The number of empty orbitals is equals to coordination number of that particular complex. So the second point, appropriate atomic orbitals S, P and D of the metal hybridized to give a set of orbitals with equal energy and definite geometry. So that is nothing but the atomic orbitals in the metal, the atomic orbitals in the metal involved in hybridization. So the metal should undergo hybridization, or the atomic orbitals of the metal should undergo hybridization to have equal energy and a definite geometry. If at all, if it is having equal energy, then they should undergo hybridization. So for hybridization, the orbitals involved will be S, P and D orbitals will be involved. So we said that how many orbitals, vacant orbitals, how many vacant hybrid orbitals should be there? It should be equal to coordination number. So if at all, if the coordination number is 4, if it is 4, then the geometry is tetrahedral. That is nothing but hybridization is sp3 hybridization. So if at all, if coordination number is 4 and the geometry is a square planar, then the hybridization will be DSP2 hybridization. So if at all, if it is trigonal bipyramidal, so here you should write it as trigonal bipyramidal, then the hybridization will be sp3d, 5 orbitals, 5 it is 1, 3, 4, 4 plus 1, 5. So here 1, 2, 2 plus 2, 4. So likewise, if at all, if coordination number is 5, then it is sp3d hybridization. It will be having a geometry trigonal bipyramidal. Likewise, if the coordination number is 6, then it may, the hybridization may be sp3d2 or it may be d2sp3. Already we have written that one in our earlier class also we have discussed. It is d2sp3. The geometry will be octahedral. So write here as octahedral. d2sp3 or sp3d2 or d2sp3. So the geometry will be octahedral geometry. So remember this one properly. So if at all, if it is sp3d2, then S is of 4s, P is of 4p, D is of 4d. d2sp3, S is of 3d, D is of 3d, S is 4s, P is 4p. It is inner orbital and it is outer orbital. Here also same thing. It is 3d, 4s, 4p, 4s, 4p, 4d here. So it is inner d and this is outer d orbital. So remember these things properly. So still few more points are there. We'll write that one also. The d orbitals involved in the hybridization may be either inner d orbitals or outer d orbitals. So if at all, if the inner d orbitals are involved, already we have seen few hybridization, that is d2sp3 or dsp2. All these are inner d orbitals involved hybridization. If at all, if it is outer d orbitals, then it is sp3d or sp3d2. So inner d orbitals will form if d orbitals are inner d orbitals, then the complex formed as inner orbital complexes. If at all, if outer d orbitals are involved, that is nd, then then the complexes are called as outer orbital complexes. Each ligand has at least one orbital of donor atom containing a lone pair of electrons. So that is ligand. We know that ligand is going to donate a pair of electron. So the lone pair of electron, the orbital of that particular ligand. So one orbital will be containing a lone pair of electron. So this is ligand consisting of a lone pair of electrons. So the empty hybrid orbitals of metal ion overlap with the filled orbitals of the ligand. That is nothing but so filled orbital in the sense, so the ligand will be consisting of a lone pair of electrons. So those lone pair of electrons, whatever the electrons are there in that particular orbital, will overlap with the empty hybrid orbitals of metal ion to form metal ligand coordinate covalent bond. So remember, it is an coordinate covalent bond has been formed between the metal and ligand. All these are the postulates according to VBT. So first two we have already studied, that is based upon the number of empty orbitals, which is equals to coordination number. So metal consists of number of empty orbitals, and those number of empty orbitals will be equal to coordination number of the metal. Next one is regarding hybridization. So hybridization will leads to the equal energy orbitals, which gives rise to definite geometry. So the third one is in the hybridization, either it may be inner d orbitals or outer d orbitals will be involved in the hybridization of metal orbitals. Next one is a ligand should contain a lone pair of electrons. So that one orbital which is consisting of lone pair orbitals will be overlapping with the empty hybrid orbitals of metal to form metal ligand coordinate covalent bond. So this is about CFT. So we have this is about valence bond theory, that is VBT. So next this extended part, all these are the postulates. So based upon these postulates, we are going to check now how the bond is being formed. By using all these details, by using all these basic ideas, we are going to check now how the bonding is being formed in the complexes, and what hybridization it is showing, what are the magnetic properties it is exhibiting. So we have 4 examples of it, and those 4 examples we are going to study each one by one in detail. In detail we are going to study about that one. So, and all these 4 are very, very important, as I said in the beginning. So in the question paper we have 2 questions of coordination chemistry part C. We have 2 questions. In that, the first question is based upon these 4 examples itself. 4 complexes we have. So in that, only one complex, among 4 only one complex will be given. So that complex hybridization, magnetic properties, and how it is undergoing, how it is forming the bond with the ligands, we should explain that one. Whether it is an inner orbital complex or outer orbital complex, what is the hybridization, what is the geometry of that one. So all those things we need to explain that one. For that, each carries 3 marks.